Mungu ibariki Tanzania, dumisha uhuru na umoja wake kwa waume na watoto. Mungu ibariki Tanzania na watu wake. Ibariki Tanzania, ibariki Tanzania, tubariki watoto wa Tanzania.
How are you, everybody who is watching this fantastic program? I would like to take this opportunity to welcome all our national, international, and even local students to join us into this program. My name is Olenjolain, Mokota Yellow Single. Simply just call me Olenjolai. I will be your physics teacher in this program. I'm a Tanzanian, so I'll be using the syllabus of United Republic of Tanzania. And I would like to take this opportunity to welcome all the students to join me into this fantastic moment of learning. So, you're only welcome into our Tanzania Online Advanced Secondary School in square bracket OLENJOLAIM. Simultaneously, we'll take this opportunity to introduce you for the first time. If it's your first time, if it's not your first time, we remind you that we have our official YouTube channel that's called Tanzania Online A-Level Secondary School in square bracket OLENJOLAIM, where we used to publish all our contents. We have so many departments, more than 3 departments. One of the departments is called Advanced Physics, and the subject of the days is called Advanced Physics, and this the main topic one is called electromagnetism. And we dedicate these contents to all pre-Form 6 students, Form 6 students, reciters, or Form 6 exam, QT, grade 12, teachers, physicists who love to learn and enjoy physics. And we have 3 topics in this main topic of electromagnetism. And the first topic is called magnetic fields and forces. This is session 3. It's called the motion of the charged particle in the magnetic field. So we have done 3 previous sessions, session 0, session 1, session 2, and this is session 3. So in session 2, we ended by dealing the fantastic homework, which was a computational question. And that question was asking you to compute force per unit length. So in previous, so let me just do the quick review. Quick review of session 2. So in session 2, simply we told you about determinations, or we simply talked about magnetic fields, and we talked about right hand grip rule. We talked about corkscrew rule. Then we talked about Fleming left-hand rule, but before we talked about the Fleming right-hand rule, we talked about straight conductor, and then we talked about the long solenoid. Then we talked about the circular coil, long solenoid. Talked about circular coil. And then we talked about after teaching about straight conductor, it means directions of magnetic field and directions of the magnetic field in the solenoid, direction of magnetic field in the circular coil. Then we talked about Fleming's lefty-handed rule. Then we told you about factors affecting what? Factors affecting the magnitude of magnetic flux density. and then the magnitude of the force of magnetic force, factor affecting magnetic force, factor affecting magnetic force. So we found that force is the proportion of the length, electric current, quantity of charge, quantity of charge, dimension of length, electric current, magnetic flux, and sign of the angle between a conductor and magnetic field. But we say if the angle is between normal of the conductor and the magnetic field, so we say magnetic force is the proportion of the length, current, magnetic flux, cosine of angle alpha. Then we left the question, which is example 1. A long straight conductor or wire, is it example 1 or 2? Carrying a current of 6 ampere lies at right angles to the magnetic field of 2.5 Tesla. Find the force per unit length of the wire. Okay. So find the force per unit length of what? Of the wire. So let us do correction of example 1. Is it example 1 or homework 2? So the first step, let us note the data which have been given. We'll be given what? Current of 6 ampere. Current, which is I, is equal to 6 ampere. Then we'll be given what? Magnetic flux density. So magnetic flux density. Magnetic flux density, which is 2.5 Tesla. Right? And then we'll be given what? Find the force on the wire. Yes, find the force of the wire per unit length. So force per unit length, this is required. So the second step, let us recall the formula. So recall. So you have either to recall force is equal to magnetic flux density times current times length sine of angle theta. If the angle is not given, so you have to assume. So assume the angle is 90. For this case, the angle between a conductor and the magnetic field is 90 degrees. Because sine of 90 is what is what. So we say that force is equal to magnetic flux density times electric current times length. Then sine of what? Sine of 90, or maybe sine of theta, like this one. But we are not asked to find the force. We have asked to find force per unit length. So we have to divide by length to both sides. So on the left hand side we have force over length is equal to magnetic flux times electric current sine of angle theta. So what the magnetic flux is 2.5 Tesla multiplied by electric current, which is 6 ampere. Then sine of 90 is 1. So this is 5 over 2, so is equal to 15 Newton per meter. Right? This is the force. So therefore, say force per unit length. Force per unit length is 1.5 Newton per meter.
15.
Are we together?
15.
Yeah, 15 Newton per meter. So we have again the next example before we go into the next 3 concepts. And then we dive again into more examples. This is example 2. A wire carrying a current of A wire carrying a current of 10 ampere and 2 meter. 2 meter in length is placed in magnetic field density. Placed in magnetic field density of 0.15 Tesla. Find the force on the wire when placed A at right angle to the field, B along the field, and C at 60 degrees to the field. So we have that question, which is titled as example 2. For this sequence, we'll be doing some more questions in this session 3 that will be testing us about the knowledge of magnetic field. So a wire carrying a current of 10 ampere and 2 meters in length is placed in magnetic field density of 0.15 Tesla. Find the force on the wire when placed from an A at the right angle to the field, right angle between a current carrying conductor and field, along the field at 60 degrees to the field. Solution. So the first step is a step that most students can ignore. It's a step of data given. Okay. So we have what? Current, which is I, is equal to 10 ampere. Then we have what? Length. Length of conductor, which is symbol L, which is equal to 2 meters. Then we have what? Plus magnetic field density. So magnetic flux density. Magnetic flux density, which is B, is equal to 0.15 Tesla. Find the force on the wire. So force on the wire, this force is required at what? At right angle to the field. So we have from an A when theta is equal to 90. So the second step, the formula which can help us to get force which is required, we have to recall the force is equal to magnetic flux density length sine of angle theta. So the force in Roman A is equal to magnetic flux density, which is 0.15 Tesla, multiplied by current, which is 10 ampere, multiplied by length of conductor, which is 2 meters, then sine of 90. So for Roman A, the force is So if you have to use your scientific calculator, you'll find the force is 3 Newton. Force is 3 Newton. B. We have to find the force along the field. What does it mean? So the force along the field. Suppose that, so this will be the steady state. You have to understand the meaning of the along the field. Suppose that these are the magnetic fields. These are the magnetic fields. Okay, magnetic fields due to the current carrying conductor, magnetic fields from the maybe from a magnet. So when the gamma conductor is perpendicular, our triangle should be perpendicular this way. When the conductor will be along the field, it means that suppose that this is the conductor. This is the conductor that is being placed in magnetic field. If we use 2 So for that case, means for this case, angle theta is equal to what? So angle theta is equal to 0 degrees. Or theta is equal to 0 degree. Okay? So the angle between a conductor and magnetic field is 0. So if that's the case, we go into the fourth state. The fourth state. So it's the force is equal to magnetic flux density, current times length, sine of angle theta. So force is equal to what the magnetic flux density. It is 0.15. Times current, which is 10, times length, which is 2, times angle, which is sine of 0 degree. So the force is equal to 0.15 times 10 times 2, sine of 0 is 0. So 0 times all of this, the force is equal to 0 Newton. So the answer for Roman B is this one. Force is 0 Newton. Okay? So 0 Newton. Then we have Roman C. Roman C at angle of 60. So it means that the conductor, the carrying conductor, is at 60 degrees to the field. So for this case, angle is 60 degrees. So the first state, we say that we have to recall what? Okay, no need to recall. The first step means let us compute it. Let's compute force. So magnetic force is equal to what? Magnetic flux density, which is 0.15, times current, which is 10, times length, which is 2, times sine of 60 degrees. So you have to use your scientific calculator. Sine of 60, it's a special angle, if you do remember. So then if you do that computation, we get this 2.598. 2.598. So therefore, magnetic force, or let's say force, as force. Force for Roman C is 2.598 Newton. That is all about example 2. So after covering example 2, let me teach you about derivation of what? derivation formula that determines the velocity of current carrying conductor of a conductor. Say that. Of a conductor in the magnetic field. So, in some cases, especially that some of the numerical problems will be given a velocity, and then you have to use that parameter velocity to find the force. And this is the velocity that will be moving a conductor placed in magnetic field. So we have to follow a few steps. The first step we call the general formula. Called the general formula of what? Of magnetic force. Magnetic force. So you say force is equal to magnetic flux density times electric current times length size of radio theta. So this is the first formula. The second step we call the formula that relates current, quantity of charge, and the current. So in electrostatic, we told you that the quantity of charge, Q, or maybe whatever it may be Q, capital Q or lowercase q. So Q is equal to current times current. So suppose that this is just equation. So you can make current here the subject. So divide by time, quantity of charge over time is equal to current. This will make second equation. Then we go into the steady state. So in the steady state, we say that substitute equation 2 into equation 1. So we are looking for the force is equal to magnetic flux density. Instead of current, we have quantity of charge over time multiplied by length sine of angle theta. So if you open bracket, we have force is equal to magnetic flux density times quantity of charge times length over time sine of angle theta. So we have magnetic force is equal to magnetic flux density times quantity of charge, and here we have length over time, then we have sine of angle theta. Okay, so given the case, we say that length over time, this is equal to velocity. So magnetic force is equal to magnetic flux density times quantity of charge times velocity times sine of 40 into theta. This is the first form of this formula. But again, we say that if quantity of charge is equal to electronic charge, means that it's a single electrons that have been moving or it's been taken into consideration. So I say that force is equal to magnetic flux density times electronic charge times velocity, then sine of angle theta. But what if the angle between the conductor and the magnetic field is 90? So from that fact, we say that if theta is equal to 90 degrees, then magnetic force is equal to magnetic flux density times electronic charge, which is symbolized as what as BEV, sine of 90, which is 1. So this may be the formula. Okay, if you have any question about what I'm teaching you today, don't hesitate to ask your question in the comment section below. Okay, so that's all about the velocity. So it means that, for example, if you want to make velocity the subject, so velocity is equal to magnetic force over magnetic flux density times electronic charge, maybe times what is sine of the angle if it's there. Okay, so that's a simple business that you have to do. So let me teach you about property. What are the properties of these magnetic fields? Properties of magnetic field. Before I teach you about the motion, before I come into today's, because I know that you are still wondering, the title of session, there is motion of the charged particle in the magnetic fields. So properties of magnetic fields. Properties of magnetic fields. Properties of magnetic fields. Magnetic field lines. Any tangent to the magnetic field lines represents directions of the field. Magnetic field lines. So the first property says that any tangent line at any point, any tangent line at any point of magnetic field lines represents what? Represent the direction of what? Of magnetic field. So any tangent line at any point of magnetic field line represent the directions of what? Of the magnetic field. That's the first property. The second property of magnetic field lines, we say that if magnetic fields are many on the unit area, so we say that if magnetic field lines are highly concentrated over the region, then it indicates strong magnetic field. Strong magnetic field, and vice versa. Vice versa. And we say that the magnetic field lines magnetic field line never cross. Magnetic field line never cross with each other. So magnetic field lines never cross each other. So they are, in most cases, parallel to each other rather than crossing each other. So I can find some more properties of magnetic field lines. Those are just a few. And ladies and gentlemen, let me teach you now the concept of motion of charging. Motion of the charging particle in the magnetic field. Motion of the charged particle in the magnetic field. So when a charged particle is moving in magnetic field, it can this charged particle it can move at right angle with that magnetic field or at a certain angle. So I won't teach you about the movement or the derivation of the formula when the charged particle is moving in the magnetic field at a certain angle. But I'll just teach you the motion of the charged particle in the magnetic field when the angle between the charged particle and magnetic field is right angle. So let's say that when a beam of electrons, moving at the right angle, so moving at right angle to the uniform magnetic field, then the charged particle describe the cycle, the uniform cycle. So when a beam of electrons moving at right angle to the uniform magnetic fields, then the charged particle describes the uniform cycle. So what does it mean? Suppose that we have uniform magnetic field lines like this. So here it is. So suppose that this is the charging particle, which is electron. So here we have a constant radius. Hence, when this charging particle is experiencing the circular, suppose that this is point P, so you can find that, for instance, at this point, which is point Q, this charging particle, there's a force that maintaining it to move in the circular path, and this force we call it centripetal force, and then the force that also maintaining it to describe the circular path, and this we call it magnetic force. So you have centripetal force that always will be attracting this body toward the center of the cycle, and also you have magnetic force, which always is kind of pushing the body away from the center of the cycle. So in order for the charged particle to describe the constant cycle or uniform cycle, these two forces has to balance, right? So magnetic force, which is due to these magnetic field lines. So remember that these are the magnetic field lines. These are magnetic field lines. So these are magnetic field lines, and this is what we call the trajectory. This is cycle, but in physics we call it this is what trajectory. So this is called the trajectory. So it's a path. So trajectory of the charging particle, which is a trajectory describes what a cycle. So I say that in order for the charge D, in order for the charge D particle to describe the circular, describe the circular motion, the centripetal force and the magnetic force should be at equilibrium. So in order for the charged particle to describe the circular motion, the centripetal force and magnetic force should be at equilibrium. Okay. So the derivation of the formula, we say that. Okay. So we say that this the rule. The centripetal force should be equal to magnetic force. Okay? Okay, so let's say this is the first step of our derivation. The second step, if that the fact, recall the formula of what? Of finding centripetal force in the mechanical. So I told you that centripetal force is equal to mass of the particle times square of the velocity over radius. Then the third step, we have been teaching you in previous session, especially session 2 and the beginnings of session 3, that magnetic force, this is equal to magnetic flux density times electric current times length. Okay? or just we can recall the other ones which are dealing with sorting. Because when we say this motion of the charged particle, in most cases we talk about electrons. So we can recall this formula, F, like this. So we have two formulas. So we can derive this one without an angle, and then so we can refer, or we can derive another formula with an angle. Because if you don't have an angle, then this is the simple derivations. But if the angle is taken into consideration, then the formula will be changing. Okay, so suppose that this is the first equation, this is the second equation, this is the third equation. So if that's the case, we say that substitute equation 1, equation 2, and 3 in equation 1. So the equation 1, we say that the centripetal force is equal to magnetic force. So we say that we have mass times velocity squared over radius is equal to it. It's equal to magnetic flux times electronic charge and velocity. So you can simplify by cancelling, by dividing by velocity to both sides. So on this side you have mass over velocity. Mass times velocity times radius r is equal to magnetic flux density times electronic charge. So in most cases, this formula can give us different physical quantity, but the most interesting one is the radius of the cycle. So we can make the radius of the cycle the subject, this. Then on this side we have mass of the electrons times velocity, then times is equal to magnetic flux density times electronic charge times radius of the cycle. So divided by magnetic flux density times electronic charge, divided by magnetic flux density times electronic charge. So radius of the cycle is equal to mass times velocity, and then over magnetic flux density times electronic charge. So this is the simple formula that can help us to find the radius of the cycle described by the charged particle, where m is the mass of electrons. So whereby m in most cases is mass of what? Mass. Okay, preventing mass. We'll see in the questions if m is what. Then v representing velocity. Then we have V, representing magnetic flux density, and A representing electronic charge, which is 1.6 exponent negative 19 coulomb. And R representing what? Radius. So R representing radius of the cycle. So this is in case that we are dealing with radius. But again, we can deal with this. Formula. Let's say force system. We can find out. We can derive the formula. Write the formula of what? Of frequency. Of finding frequency. Because that charged particle will be describing frequency, so number of revolution per second. Will be describing rotational motion. So we say that first of all, we have to say that from the fact that linear velocity is equal to angular velocity times radius of the cycle, and also from the fact that angular velocity is equal to 2 pi times frequency, and then radius r. So we can call this one as equation 4. If you refer from beginning. Then so you have radius is equal to what? Radius of the circle is equal to mass times velocity over magnetic flux density times electronic charge. So this is question 5. So the fifth step, we say that substitute equation 4 into question 5. So radius of the cycle is equal to mass. What's linear velocity is 2 pi frequency, then we have radius of what? Magnetic flux density times electronic charge. So radius and radius cancel. Let us make frequency the subject. So on this side we have 1. So you still have 1, 2 mass pi frequency over magnetic flux density times electronic charge. So because you want to make here we have 1 over 1 frequency the subject. So frequency is equal to magnetic flux density times electronic charge. Then you have what? You have 2 mass times 40 times pi. 2 pi. So frequency is equal to magnetic flux density. So frequency is equal to product of magnetic flux density times electronic charge, 2 pi mass of 40 of electron. But also in some cases, for example, in cyclotron, certain vocabulary failed to pronounce. Yes, cyclotron. So in some cases of cyclotron, we can find that we need to find kinetic energy. So we know kinetic energy is equal to a half times mass times square of the velocity. So we have to make velocity the subject from this formula, from equation 5, in order to substitute it for the computations of kinetic energy. So you say that from radius is equal to mass times velocity of what? Magnetic flux density times what? Electronic charge. So make velocity the subject. So you say radius is equal to mass times velocity, magnetic flux density times electronic charge, magnetic flux density times electronic charge, magnetic flux density times electronic charge. So magnetic flux density times electronic charge times radius is equal to mass over velocity divided by mass. So final velocity or velocity is equal to magnetic flux density times electronic charge times radius over mass of the charged particle. So this formula might be helpful in the future. Okay. So when a charged particle will be describing or will be moving, consider particle of this one, moving as the velocity of this one is the electromagnetic field. So we say if the charged particle enters the region of magnetic field at certain angle, given angle theta, then it describes helicopaths. So we describe helicopaths. So if the charged particle enters the radius of magnetic field at a certain angle theta, then it describes what? It describes helicopaths. So in this case, we say that the formula will be from centripetal force is equal to magnetic force. So the centripetal force is equal to mass times velocity in vertical component square over r is equal to magnetic force. So you say vertical component means the centripetal force will be mass over radius, and then here we have velocity times sine of angle theta square. While the magnetic force, we have magnetic flux density times electronic charge times velocity, and then sine of angle theta, where this is the angle between a conductor and what, or between this is the angle between a charged particle, because when you say it is a helicopath, suppose that these are the magnetic field lines. So this is the point where the charged particle enters. So you see that this is the point, so there's an angle theta. Right? So we assume this helicopath that in some parts it's a cycle, but this is assumption, but it's a cycle whereby the velocity is we consider it as the vertical component and horizontal component, because this is just like a trajectory. That's what we call it, trajectory. If just you consider this part itself, you can find that this velocity has both vertical and horizontal component. Okay? So if that the case, we say that okay. So we simplify velocity sin theta. On this side, the remaining is mass times velocity sine of angle theta over radius r is equal to magnetic flux density times electronic charge. So you can derive some other formulas from this formula. So because means that the primary interest in the relations of this formula, we have mass, velocity, sine of angle theta over radius. This is equal to magnetic flux density times electronic charge. So radius is equal to magnetic flux density times electronic charge. Then here we have mass times velocity, sine of angle theta. Okay? So this is the formula for the radius if the angle is not right angle. So you can also use the same formula to derive the formula for the frequency and also derive the formula for the velocity. Also note the following. Kinetic energy is equal to a half times mass velocity square. Vice versa. So I made a mistake here. It is mass times velocity sine of angle theta over magnetic flux density times electronic charge. Okay. So you say that this is formula for what? For the kinetic energy. It's equal to half times mass of the charged particle times square of the velocity. But also from modern or from atomic physics, we just give you this. We'll discuss later on when we'll be discussing about instance, kinetic energy, also the charged particle, even in electrostatic introduces, is equal to electronic charge multiplied by accelerating potential. So thereby E is equal to electronic charge, then VA, this is equal to accelerating potential. Okay, so if that's the case, let us go into example 3. If there is any question, the online student please ask in the comment section. If there is no any question, then let us continue. Protons with charge to mass ratio of 1.0 exponent 8 Coulomb per kilogram are revolved in a circular path. Are revolved in circular paths of radius r. When they enter the uniform magnetic field, are revolved in the radius r. When they enter the uniform magnetic field. When they enter the uniform magnetic field of 0.5 Tesla on R, show that the number of revolution per second is independent of R. D. Calculate frequency. So let us read the question. Protons with the charge to mass ratio of 1 exponent 8 Coulomb per kilogram are revolved in circular paths of radius r. When they enter the uniform magnetic field of 0.5 Tesla, Command A, show that the number of revolution per second is independence of radius, and B, calculate frequency or 40 or a product. Solution. Still simple question. You can pause the video and try it. Just to stay. This is the data given. So we have charge to mass ratio. Charge to mass. So which is quantity of charge, Q to mass is equal to 1 exponent to 8 Coulomb kilogram. Then a revolving circular path of radius r. Then we have magnetic flux density. Magnetic flux density is equal to 0.5 Tesla. Show that the number of revolutions per second. So what does it mean? Frequency. Show that the number of revolutions per second is independence of radius r. Then B, we have to find frequency. So you can find the question of Roman R depends on the questions of Roman B. So if that's the case, we say that, okay. So in describing a circular path, so circular path, so it means that these protons are stated in the radius of magnetic field. So we go into the second step. So we say that from second step, we say that we call the two forces should be at equilibrium in order for the proton to describe a circular path where the magnetic force should be at equilibrium with the centripetal force. And because it is not helical path, it is circular path, so magnetic flux density will be magnetic flux density times quantity of charge times velocity is equal to centripetal force, which is mass times the square of the velocity over radius r. So first of all, we have to show that the number of revolutions per second is dependent to the radius r. So this velocity and velocity cancel. So we have magnetic flux density times quantity of charge equal to mass times velocity over radius r. Okay, so this makes our first equation for this problem solving. So we go into the third step. So the step say that we have to recall that linear velocity is equal to angular velocity times radius r. Angular velocity is equal to pi frequency times r. So here we say that velocity is equal to 2 pi frequency times radius r, and this makes equation 2. So we say that the first state, substitute equation 2 in equation 1 by so we have magnetic flux density times quantity of charge is equal to mass 2 by frequency r over radius. So radius cancel. Magnetic flux density times quantity of charge is equal to 2 pi mass times frequency. So We want to make frequency the subject, so you have 2 pi mass frequency. So you have frequency or number of revolution per second is equal to magnetic flux density times quantity of charge, or quantity of charge of protons over 2 pi mass of 40 mass of proton. Okay, mass of proton. So you have protons with charge to that one still to m. Okay. So therefore, hence shown. So this is number A. So hence shown that frequency is independent of radius. Why it's independent? Because in the final formula of computing frequency of a charged particle of proton, we don't have any variable of radius on right hand side. So you have magnetic flux density, we have quantity of charge, we have 2, we have pi, we have mass. So radius has been cancelled along the line of derivation. So from this fact we say that frequency is independent of what? Radius of the cycle. So the number of revolution per second described by the charged particle moving in magnetic field is independent of what? Radius of the cycle. So whether the radius of the cycle is big or the radius of the cycle is small, then the number of revolution per second will be the same. That means independent from what? From the radius. So B, we have to compute the frequency. Okay. So this is the first step. So the first step, you have to recall the formula that we have already derived. That frequency is equal to magnetic flux density times quantity of charge 2 pi times mass. So we are finding, we will be asked to compute the frequency. So frequency is equal to magnetic flux density over 2 pi, and then we have to multiply with charge to mass ratio. We will be given here protons with charge to mass ratio Q to M. Q to M. So to compute the frequency for this case is equal to magnetic flux density, which is 0.5 Tesla, then divided by 2 pi, which is constant, multiplied by charge to mass ratio, which is 1 exponent 8 coulomb per kilogram. So that will give us number of revolution per second, which it is 7.958 when you use your scientific calculator. So you say that the number of revolution per second, we say that, or the frequency of proton is 7.95958 exponent 6 per second, or hertz. Or in other words, you say that is 9, or say it is 97.958 megahertz. So you see the frequency is high. It's megahertz. After the frequency of the protons in magnetic field is high. So that's how you do your computation. So example 4. An electron is emitted by a heated cathode and accelerated through potential difference. Through potential difference. Through potential difference of 2 kilovolt enters a region of magnetic fluxing magnetic flux density of 0.5 Tesla or 0.15 Tesla. 0.15 Tesla. Okay. For A, find the trajectory of the electron. Find the trajectory of the electron. Find the trajectory of the electron if the field is domain 1 transverse. To its initial velocity. Transverse to its initial velocity. Then 1 and 2. Find the trajectory of the electron if the field makes an angle makes an angle 30 degrees with initial velocity. So an electron is emitted by a heated cathode and accelerated through a potential difference of 2 kilovolt, enters a radius of magnetic flux density of 0.15 Tesla. Find a trajectory. What the means of trajectory? Trajectory of electrons if the field is Roman 1 transverse to its initial velocity. Roman 2 makes an angle of 30 degrees with initial velocity. That's the question we have on the spot. How can we solve this problem? Find the trajectory at the first vocabulary. What it means of trajectory. How do we measure trajectory of a particle? Solution. The first step, which is common, however, that many advanced secondary students might ignore it, but it will cost them. We have accelerating, so the potential difference of 2 kilovolts. So you have accelerating potential of 2 kilovolts. So you have potential difference which can call to V or PD, just differentiate with velocity. This is 2 kilovolt, which means that it's 2000 volts. Then we have what? We have magnetic flux density. Magnetic flux density. Magnetic flux density, which is B, is equal to what? Is equal to 0.15 Tesla. 0.15 Johnson. So Johnson, you are Johnson. 0.15 Tesla. And then we've been asked to find trajectory. So trajectory is required. Okay. This trajectory is required when the transverse, what I mean so transverse, at right angle, transverse, to its initial velocity. And as if the charged particle makes an angle of 30 degrees with initial velocity. So transverse means at right angle or means perpendicular. So what the means of trajectory first of all? So we go into the second step and grasp the meaning of trajectory first. So the second, so you say that consider the figure below. So we have uniform, suppose that we have uniform magnetic fields. So uniform magnetic fields like this. So we have uniform magnetic fields like this. And then we have, let's say, the charged particle that describe a circular path. And hence, this is if its angle of interest is 90 degrees. So this is what we call the trajectory. So how do we measure trajectory of a charged particle? So trajectory means it's a circular path, so it's helical path. So we measure trajectory by using what? Radius. The magnitude of trajectory is defined by the radius of 40 of the circle. So when we have been asked to find the trajectory, it means we have been asked to find the radius. A radius of the circle if it's right angle, and radius of the helical path if it's not 30 but right angle. So the same thing. So to find the radius, but we don't know the velocity first of all of this charged particle. We don't know it. We don't know its velocity. So the first step we say that compute velocity of electron. Velocity of electron. So velocity of electron, how can we compute? have to remember some formulas that I gave you before we solved example 3. And that formula, I told you that kinetic energy is equal to a half times mass of electron times square of the velocity of electron. Also, kinetic energy is equal to what? Is equal to electronic charge times what? Accelerating potential. So this is the formula that will give us velocity of what? Velocity of electrons, because these electrons is describing a circular path, so it has a constant velocity that enable it to describe a circular path. So here we have a half times mass velocity square, then electronic charge times what? Accelerating potential. So we multiply by 2, and we multiply by 2, so we have mass times velocity square is equal to twice times electronic charge times accelerating potential. So divided by mass of electron, then divided by mass of electron. So this side cancels, so we have square of the velocity equal to 2 times electronic charge times accelerating potential for mass of electron. So this will give us what? Velocity. Okay. So for Roman 1 again. So this will give us third state, first state. The first state, we say that if an electron is describing a circular path, then the force of centripetal should balance with magnetic force. So centripetal force for Roman 1 will be mass times velocity square over radius is equal to magnetic force, which is magnetic flux density times electronic charge times velocity. So velocity and velocity cancel. So on this side we have mass over velocity times radius is equal to magnetic flux density times electronic charge. So this is over 1, so we cross multiplication. You can find what is radius. So if we cross, we have what? Mass times velocity is equal to what? Magnetic flux density electronic charge times radius, or magnetic flux density electronic charge, magnetic flux density of electronic charge. So radius is equal to what? Mass times velocity over magnetic flux density times electronic charge. So this is equation 2. So if we make velocity here, we can find the square root to get velocity itself. So radius of the cycle, if electrons enter at the transverse, is equal to what? Mass of electron over magnetic flux density times electronic charge times velocity, which is the square root of what? Square root of twice electronic charge, accelerating potential over mass of what? Of electron, like this. Okay? So Roman 1, we have radius is equal to mass of electron, which we know is 9.1 exponent negative 31, if I'm not mistaken. Yes, 9.0. So negative 31 over magnetic flux density, which is 0.215 times electronic charge, which is 1.6 exponent negative 19. Then we say square root of 2 electronic charge is 1.6 exponent negative 19. Then accelerating potential is what? 2000 divided by mass of electrons, 9 exponent negative 31, like this. So then radius is equal to, it is 1 exponent. If you do your computation, it's 1 exponent negative 3 meter. 1 exponent negative 3 meter, which simply is equal to 1 millimeter. So therefore, for only one trajectory is what? 1 millimeter. Okay. That is, if an electron enters at right angle with the magnetic flux intensity. So that is which is step number 4. This is step number 5, substitution. Substitute equation 1 into equation 2. So here it is, we are in Roman 2. So in Roman 2 we have an angle of 30. We have an angle of 30. So if you have an angle of 30, we say that this should be what? 660. Centripetal force has to balance with magnetic force. So centripetal force for this case will be mass, velocity, sine of angle theta square, radius r. And magnetic force should be magnetic flux times electronic charge, velocity, then sine of angle theta. So you simplify this in one term. So here you have the mass and velocity, sine of angle theta over radius r. We have is equal to what? Magnetic flux density times electronic charge. So our interest, we are looking for it. We are looking for the radius. So we have here 1. So in cross multiplication, we make radius is equal to mass times velocity sine of angle theta over what? Over magnetic flux density times electronic charge. So this will make equation. So you have equation 1 that will help us to find velocity. Or sometimes you can compute velocity itself and then substitute. You are not limited to use that alternative. It depends which one is the simplest way for you. So the 7th step, we say that substitute equation 1 into equation 3. To equation 3. So we have radius is equal to what? Mass of electron, sine of theta over magnetic flux density times electronic charge. Then you have square root of that. Twice electronic charge times accelerating potential, then over mass of electron. For that case, we have radius is equal to what? Mass of electron, 9 exponent negative 31. Sine of angle is sine of 30 degrees. Magnetic flux density 0.15. Electronic charge 1.6 exponent negative 19 times twice. Electronic charge 1.6 exponent negative 19. Accelerating potential is 2 solar. Then our mass of electrons is just 9 exponent negative 31. So if you do your computation, you get the trajectory is 5.06 for -4 meter. So the answer for number 2 trajectory is 5.06 exponent -4 meter. If you didn't get that, then you have to check your computation. That is example 4. So let me present to you example 6. Example 5, excuse me. Example 5. This is concept. You have to be careful when you're solving it. A wire W of length (0.1 millimeter), resistance 0.1 ohm, and mass 5 exponent -3 kilogram, is free to move. It's free to move along the rails. Along the rails of negligible resistance as shown in the figure below. The wire is at right angle wires at right angle to a uniform magnetic flux density uniform magnetic flux density of 0.4 Weber per meter directively into the plane containing the rays. Roman 1. Determine the initial acceleration of the wire when a battery of 2 volt and the internal resistance of 0.1 ohm is connected between ends P and Q. This positive terminal. Positive terminal on P. A wire W of length 0.1 millimeter, resistance 0.1 ohm, and mass of 5 exponent negative 3 kg is free to move along the rails of negligible resistance, as shown in the figure below. The wire is at right angle to a uniform magnetic flux density of 0.4 Weber per meter square, directed into the plane containing the rails. Then Roman 1, determine the initial accelerations of the wire when a battery of 2 volt and internal resistance of 0.1 ohm is connected between ends P and Q with positive terminal on P. How can you find it, or how can you solve that problem? Okay, so it seems like a question is a little bit challenging. Let us read it again. A wire W of length 0.1 millimeter. Okay, we have length of the wire. And resistance of 0.1 ohm. Okay, we have resistance of the wire. And mass of 5 exponent negative 3 kg is free to move along the rails of negligible resistance are shown in the figure below. The wire is at right angle to a uniform magnetic flux density of 0.4, so it is uniform. It's at right angle, so it's describing something else, or particular motion. Directed into the plane containing the rails. Okay, containing the rails. Roman 1. Determine the initial acceleration of the wire when the battery of. We have Roman 1. Yes, no need of Roman 1. The question is just 1. We have determined the initial acceleration of the wire when a battery of 2 volt and internal resistance of 0.1 ohm is connected between P and Q with positive terminal on P. So this is the figure, these are the rails, and the wire is sliding over this. And that's because these are the current carrying conductors. When it's a current carrying conductor, there is a magnetic field which will be produced. So you can pause the video and try to solve this question on the rough paper, and you'll come and check the solution if you have succeeded to find the right solution for calculation. If you missed it somewhere at the process of doing exercise or of doing practice before the magic solution. It seems the question is difficult. It is, but try your level best to simplify it. That's why you're a physicist. So the first step that are given, I know for most students, even here they write data because they know actually this is a little bit challenging question. So the first piece of information be given is length of conductor. So the length of conductor, which is equal to R, is equal to 0.1 millimeter. So you can express it in, it's just a unit, it will be 1 exponent negative 4 meter. Okay? Then you'll be given the resistance of the wire. Resistance of the wire, which you use the capital R. It's 0.1 ohm. And then we'll be given mass of the wire. Mass of the wire. This is 5 exponent negative 3 kilogram. It's free to move along the rails of negligible resistance as shown in the figure below. The wire is at right angle to a uniform magnetic flux density of that one. So we have magnetically flux density, which is B, is equal to what? Is equal to 0.4. Just like, because 1 over meter square means this one. Then you have what? Erected into the plane containing that one. So determine the initial acceleration. So initial acceleration is what you are looking for. So initial acceleration, which is A, is required. So the potential difference, the electromotive force, the EMF, this is equal to 2 volt. Then the internal resistance, R is 0.1 ohm. So you have to find initial acceleration. That's the first step, which is not difficult for every student. You have just to read the question carefully. The second step now, we say, okay, you have to record this fact. Second step, we say that if the wire accelerates accelerate along what? Along the magnetic field. Magnetic field. So if the wire accelerates along the magnetic field, then the accelerating force should be equal to the magnetic force. So this wire is not describing a circular path, it's describing a linear path. So I say that the accelerating force, which is linear force, always will reach at equilibrium for this wire to accelerate on those rails is equal to magnetic force. You have to be careful. So accelerating force for this case, according to the Newton's second law, it's mass times acceleration. This is equal to magnetic force, which means this magnetic flux density times current times length sine of an angle theta if the angle is there. But because no any questions that actually talks about the angle, yes, there is a piece of information. So it means the y is a right angle. So sine of 90 is 1. Okay, sine of 90 is 1. But sine of 90, which means right angle is 1. So we say that the mass of a wire times its linear acceleration or initial acceleration is equal to magnetic flux density times length times current times length of 40 of the wire. And this will make the distinction. Then, second state or steady state. So the steady state, we say that from the formula that we told you for the first time during the Form 2 education, that electromotive force of the battery, this is equal to electric current multiplied by external resistance or the external resistance plus internal resistance. So there's a relationship between question 1 and this new equation. So let me make current a subject. So we have resistance plus internal resistance. On this side you have external resistance plus internal resistance. So you find that electric current is equal to electromotive force over external resistance plus what internal resistance. And this is question 2. So to find any acceleration, we go into the first step. Say that substitute question 2 into equation 1. So you have mass times acceleration is equal to what? Is equal to magnetic flux density times length, then electromotive force, resistance plus internal resistance. Like this. So divided by mass, and here divided by mass. So the initial acceleration is equal to what? Is equal to magnetic flux density times length over mass. And this is electromotive force, external resistance plus internal resistance. So the linear force is equal to magnetic flux density, which is 0.4 times length of the conductor, which is 1 exponent negative 4. Mass of what of a wire is 5 exponent -3. Then electromotive force of the battery is 2 volt. Then we have internal extra resistance 0.1, inter resistance 0.1. So if you do your computation there, you'll find that initial acceleration is 0.08 meter per second square. Initial acceleration is 0.08 meter per second square. So that is example 5. You may do example 6 and maybe example 7 as your homework. 600 voltage is applied across the plates. Across the plates of parallel plate capacitor. Parallel plates of the capacitor. The separation between the plates is 3 millimeter. An electron is projected vertically. To the plates. The velocity of 2 exponent 6 meter per second. Find the magnetic flux density. So a 600 voltage is applied across the plates of parallel plates of the capacitor. The separation between the plates is 3 millimeter. An electron is projected vertically parallel to the plates with velocity of 2.6 meters per second. Find the magnetic flux density. It's not a difficult question. You have just to know the relationship between electromagnetism and electrostatic. So the first step is the common step. Let us analyze the data that will be given. Will be given potential difference voltage. Voltage which will be is equal to 600. Yeah, 600 voltage. So applied across the place of the applied capacitor. So here we have separation distance, which is 3 millimeter. So 3 millimeter in its unit is 3 negative 3 meter. So an electron is projected vertically parallel to the plates with capacitor, which is V is equal to 2 exponent 6. Per second. Find the magnetic flux. Magnetic flux density. So the second step, you'll be given voltage, you'll be given separation distance. It talks about capacitor. So 2 parallel plates of capacitor. What does it mean? The 2 parallel plates of capacitor. And the distance of separation, d, which is 3 millimeter. And the potential difference between these is 600 voltage. Then we have what? Then an electron is projected vertically parallel to the plates with velocity of 2 exponent 6. So we know also the velocity of what? We know the velocity of electron, and it has been accelerated in the regions of magnetic field. So, because these 2 parallel plates, so let me just think, these are the 2 parallel plates of capacitor. So suppose one plate is positive and the other plate is negative. So the distance separation, it is 3 millimeter. The potential difference or the voltage between them is 600 volts. 600 voltage. Then an electron is being accelerated. So because there's electric field from positive to negative, that's why we say that we expect also to have magnetic field. However, that's not of the large flux or of the large quantity, but we expect to have magnetic field. So the third step, because the electrons is moving in electric fields, so I say that electric force that acting to the electrons will be equal to magnetic force. Because they have magnetic fields, we have electric field, so we expect to have magnetic field. From electrostatic, the electrostatic force, so suppose that this is equation 1. The electrostatic force is equal to electric field density multiplied by the quantity of charge Q. So because the quantity of charge is electrons, so we say that it's electric field density times electronic charge. That is what we call the electric force. Then magnetic force in terms of velocity is equal to magnetic flux density multiplied by what? Multiplied by electronic charge multiplied by velocity. Because the velocity is given of electrons. So you can call this as equation 1, this as equation 2, this is equation 3. So you can go into the first simple state, the first state. So substitute equation 2 and 3 in equation 1. So electric field strength times electronic charge is equal to BEV. So electronic charge cancel. You have electric field is equal to magnetic flux density times velocity. So we make magnetic flux density the subject because that's what we are looking for. So magnetic flux density is equal to electric field density over velocity. But also we taught you in electrostatic that electric field density is equal to electric potential over distance of separation between two plates. So electric potential over distance of separating the two plates. Okay, so this one you can see that electric potential. Just let us have this symbol to distinguish it from velocity. So the first state, substitute equation 5 into equation 4. So magnetic flux density is equal to it. Electric field, which is electric potential, over velocity times distance. So what is electric potential? It's 600 voltage. Then what is velocity? It is 2. Velocity is 2 exponent 6 meters per second. What is distance of separation? 3 exponent -3. So magnetic flux density is 0.1 Tesla to such kind of the computation. Because this will make 60. Here we remain, so it will be 6 exponent 3. If you divide 600 over 6,000, you get 0.1 Tesla. So simply say that the magnetic flux density is 0.1 Tesla. Homework. The question for the homework, this will be example 6, 7, is it? Example 7, simple, very simple. A proton with charge to mass ratio, proton with mass charge to mass ratio of 10 exponent 8 coulomb per kilogram is moving in a uniform field on field of 0.5. Just calculate the frequency of revolution. Ladies and gentlemen, after giving you this homework 3, it's the end of session 3. So you have seen that the main concentrations of session 3 is to teach you about computations, just the derivation and computations of formulas or computations of different physical quantities of a charged particle that moves in magnetic field. That's it. Make sure that you do the homework and you submit in the comment section below of this video. And then make sure that you watch this video several times as well as you can and give me the feedback in the comment section whether you have understood or not, or you still have some challenges, so I can help you. So I'd like to invite you in the next session, which will be session 4, where I will teach you about magnetic torque. It will be a new concept, but it will be very interesting for you. So you have to make sure that you will be well prepared to receive and learn the new concept. And we are still following the concept that we have listed in session 0, the general introductions of electromagnetism. So stay tuned, keep enjoying, don't worry, we will cover those stuff that may be troubling your mindset if you are aware with this concept. So stay tuned and keep enjoying the beauty of advanced physics. Remember also to subscribe onto our channel because we are still in session 3. We are expecting to have more than 30 sessions of electromagnetism. So you have to make sure that you subscribe in order for you to receive notification when session 4 will be uploaded or made public, and session 5, etc., etc. So stay tuned and keep enjoying the beauty of advanced physics. See you in the next session.
Mungu ibariki Tanzania, dumisha uhuru na umoja wake kwa waume na watoto. Mungu ibariki Tanzania na watu wake. Ibariki Tanzania, ibariki Tanzania, tubariki watoto wa Tanzania.